Tonight, we're going to explore something that sounds like science fiction, but is actually hard physics and biology. Missions to Mars. You've probably seen the headlines, the plans, the bold promises about sending humans to Mars in the next decade or two. SpaceX says they'll do it. NASA has detailed timelines. Other countries are announcing their own programs. Everyone talks about going to Mars like it's just the next logical step. Like it's Apollo 11, but with a longer flight. But buried beneath all the excitement and ambitious timelines is a truth that rarely gets mentioned. Anyone who goes to Mars is probably never coming back, not due to accidents or equipment failures, but because the sheer physics of escaping Mars and surviving the return journey makes coming home nearly impossible. And by the end of tonight, you're going to understand exactly why Mars missions are really colonization missions, why the first people who set foot on Mars are saying goodbye to Earth forever, and why this isn't speculation or pessimism, but the unavoidable reality of interplanetary travel. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with why Mars seems like the obvious choice for human exploration beyond Earth. Mars is close, at least by cosmic standards. It's the fourth planet from the Sun, sitting right next door to Earth in the solar system. At its closest approach, Mars is about 34 million miles from Earth. That's when both planets are on the same side of the Sun in their respective orbits, lined up in what astronomers call opposition. At its farthest, when Earth and Mars are on opposite sides of the Sun, the distance stretches to about 250 million miles. But even at that maximum distance, Mars is vastly closer than anything else we might consider visiting. The next candidate would be Venus. But Venus is a hellscape with surface temperatures hot enough to melt lead and atmospheric pressure that would crush a submarine. Beyond Mars, you're looking at the gas giants, Jupiter and Saturn, which are thousands of times farther away and have no solid surface to land on. Mars is the only nearby planet where humans could conceivably stand on solid ground, where the temperature occasionally reaches above freezing, where water ice exists, where the day is roughly 24 hours long. It's the most Earth-like place in the solar system, which admittedly isn't saying much. Mars is a frozen desert with an atmosphere 1/100th as thick as Earth's, composed mostly of carbon dioxide. The average temperature is minus 80 degrees Fahrenheit. There's no magnetic field to protect against radiation. Dust storms can engulf the entire planet for months, but compared to everywhere else, Mars looks downright hospitable. This is why Mars has captured human imagination for over a century. In the late 1800s, astronomer Purcell Lell claimed to see canals on Mars through his telescope. He thought they were artificial waterways built by an advanced Martian civilization struggling to irrigate their dying world. He was wrong. The canals were optical illusions, but the idea took hold. Mars became the home of little green men in popular culture, the setting for countless science fiction stories about ancient civilizations or invading armies. H.G. Wells wrote about Martians attacking Earth. Edgar Rice Burroughs wrote about human adventurers traveling to Mars and finding a world of warring city-states. Ray Bradbury wrote about human colonists bringing Earth culture to Mars and the conflicts that arose. The cultural fascination never went away, and when the space age began in the 1950s and 60s, Mars became the next logical target after the Moon. If humans could reach the Moon, a journey of only 240,000 miles, surely Mars was just a longer version of the same achievement. The Apollo program landed 12 humans on the Moon between 1969 and 1972. Those missions required about 3 days of travel each way. The astronauts spent at most 3 days on the lunar surface before returning home. The entire journey from launch to splashdown took about 8 to 12 days. It was difficult, dangerous, and expensive, but it was achievable. NASA proved that humans could survive the journey, work in a hostile environment, and return safely to Earth. When the Apollo program ended, many people assumed Mars would be next. The technology hadn't been demonstrated. The capability existed. It was just a matter of building bigger rockets, carrying more supplies, and spending more money. Plans were drawn up in the 1970s and 80s for Mars missions using nuclear propulsion or massive Saturn V-style rockets. These plans assumed that Mars missions would work like Apollo. Launch from Earth, travel to Mars, land, explore for a few weeks or months, then launch back from Mars and return to Earth. Simple, just longer and bigger. But as engineers actually worked through the details, they discovered something disturbing. A Mars mission doesn't work like Apollo at all. The distances involved, the time required, the fuel needed, The physical toll on human bodies, every single factor is exponentially more difficult. What looks like a simple scaling up of Apollo turns out to be a fundamentally different kind of problem. The first challenge is distance. And while we've already established that Mars is close by cosmic standards, it's still almost unimaginably far by human standards. The Moon is 240,000 miles from Earth. Mars at its closest is 34 million miles away. That's 142 times farther than the Moon. At its farthest, it's over 1,000 times farther. This distance creates immediate problems that didn't exist for Apollo missions. The journey to Mars takes between 6 and 9 months, depending on the trajectory and the relative positions of Earth and Mars. That's not 6 to 9 months round trip. That's 6 to 9 months just to get there. The astronauts who landed on the Moon spent at most 12 days away from Earth. Astronauts travelling to Mars will spend at least 6 months in transit before they even arrive. 6 months of living in a cramped spacecraft, breathing recycled air, drinking recycled water, eating stored food. 6 months of exposure to cosmic radiation with no protection from Earth's magnetic field. 6 months of microgravity with bones losing density and muscles atrophying. Despite exercise regimes, 6 months of psychological stress from isolation, confinement, and the knowledge that Earth is getting farther away every single day. And that's just the outbound journey. Here's where the physics gets cruel. Once you arrive at Mars, you can't just turn around and come home. The orbital mechanics don't allow it. Earth and Mars orbit the Sun at different speeds. Earth takes 365 days to complete an orbit. Mars takes 687 Earth days. This means the planets are constantly changing their positions relative to each other. The launch window for travelling from Earth to Mars when the planets are positioned correctly for an efficient transfer orbit only occurs once every 26 months. And when you're on Mars, the launch window for returning to Earth also only occurs once every 26 months. But here's the critical detail. The return launch window doesn't open immediately after you arrive. If you travel from Earth to Mars during one launch window, you have to wait for the next launch window before you can return. That means waiting approximately 2 years on Mars before the orbital mechanics even allow a return journey. 2 years, 730 days. Compare that to Apollo astronauts who spent at most 3 days on the Moon, so the minimum mission duration for a round trip to Mars is approximately 3 years. 6 to 9 months travelling to Mars, 2 years waiting on Mars for the launch window, 6 to 9 months travelling back to Earth, 3 years minimum, and that's if everything goes perfectly. If no problems occur, if the return launch happens exactly when planned, any delay extends the mission by another 26 months, because you've missed the launch window and have to wait for the next one. 3 years is a long time for a mission. It's an enormous commitment, an enormous risk, and the physical toll of those 3 years makes the return journey questionable, even if it's technically possible. Now let's talk about fuel, because this is where the mathematics become truly brutal. Every rocket ever launched from Earth has faced the same fundamental constraint called the Tsiolkovsky rocket equation. This equation, derived by Russian scientist Konstantin Tsiolkovsky in 1897, describes the relationship between a rocket's mass, its fuel, and the velocity it can achieve. The basic principle is simple and devastating. To go faster, you need more fuel, but fuel has mass, so adding fuel makes the rocket heavier. A heavier rocket needs more fuel to achieve the same velocity, but that additional fuel also has mass, so you need even more fuel to carry it. This creates an exponential relationship. Small increases in desired velocity require enormous increases in fuel mass. For Apollo missions, this was manageable because the Moon has low gravity and no atmosphere. The lunar module that landed on the Moon only needed to achieve about 5,400 feet per second of velocity to escape the Moon's gravity and return to lunar orbit where it could dock, with the command module for the trip home. The fuel required for this was significant but achievable. The lunar module carried about 5,500 pounds of fuel for the descent to the surface and about 5,000 pounds for the ascent back to orbit. The entire vehicle, when fully fueled, weighed about 33,000 pounds. Mars is different. Mars has about 38% of Earth's gravity. That's much less than Earth, but it's still significant. It's roughly twice the gravity of the Moon. This means escaping Mars' gravity requires much more velocity than escaping the Moon's gravity. A spacecraft launching from Mars needs to achieve about 11,800 feet per second to reach orbit. That's more than double the velocity required for the Moon. And because of the rocket equation, doubling the required velocity doesn't double the fuel requirement. it increases it exponentially. Let's do some rough calculations. If you wanted to send a spacecraft comparable in size to the Apollo lunar module from Mars' surface to Mars' orbit, you'd need approximately 4 times as much fuel as the lunar module used. That's about 20,000 pounds of fuel just for the ascent from Mars' surface to Mars' orbit. But you also need fuel to leave Mars' orbit and travel back to Earth. That requires achieving escape velocity from Mars, which is about 11,800 feet per second relative to Mars, and you need fuel to slow down when you reach Earth. To enter Earth orbit or directly re-enter Earth's atmosphere. When you add all this up, the total fuel requirement for a Mars return journey is staggering. Estimates vary depending on mission design, but a conservative estimate suggests you'd need somewhere between 80,000 and 150,000 pounds of fuel just for the return journey from Mars' surface to Earth. That's an enormous amount of fuel, and here's the problem. You have to bring that fuel with you. Every pound of fuel you need on Mars for the return journey has to be launched from Earth, carried to Mars, and safely landed on the surface. When NASA and private companies actually run the calculations for a crewed Mars mission with a return capability, they arrive at spacecraft masses that are almost absurdly large. You're talking about mission masses of several hundred tons in low Earth orbit before the journey even begins. For comparison, the entire Apollo spacecraft, including the command module, service module, and lunar module, had a mass of about 100,000 pounds or 50 tons in low Earth orbit. A Mars return mission would require at least 5 to 10 times that mass, possibly more. Launching that much mass from Earth requires either multiple heavy lift rockets or a completely new class of super heavy lift vehicle that doesn't currently exist. It's technically possible, but it's phenomenally expensive. Estimates for the cost of a single crewed Mars round-trip mission with full return capability range from $100 billion to $500 billion, depending on mission architecture and what technologies need to be developed. That's approximately the cost of the entire Apollo program adjusted for inflation. And Apollo was the most expensive piece in government program in American history. There is a potential solution to the fuel problem called INC2 resource utilization, or ISRU. The idea is elegant. Instead of bringing all the fuel for the return journey from Earth, you manufacture it on Mars using local resources. Mars has a thin atmosphere composed of 95% carbon dioxide. It has water ice in the soil, confirmed by multiple Mars missions. Using a chemical process called the Sabatier reaction, you can combine carbon dioxide from the atmosphere with hydrogen to produce methane and water. Methane can be used as rocket fuel. The water can be electrolyzed using solar power to produce hydrogen and oxygen. The oxygen can be used as an oxidizer for the methane, and the hydrogen can be recycled back into the Sabatier reaction to produce more methane. This creates a closed-loop system that can theoretically produce large quantities of rocket fuel using only Martian carbon dioxide, water, ice, and energy from solar panels. SpaceX's Starship is specifically designed with this in mind. Starship uses methane and oxygen as propellants because these can theoretically be manufactured on Mars. Elon Musk has stated repeatedly that ISRU is essential for making Mars missions economically feasible. Without it, the cost of bringing all the return fuel from Earth makes missions prohibitively expensive. This sounds like it solves the problem, and in theory it does, but in practice ISRU introduces enormous complexity and risk. First, you need to land the fuel production equipment on Mars before the crew arrives. This equipment needs to be heavy, complex, and reliable. It needs to survive landing, deployment, and continuous operation for at least 2 years in Martian conditions exposed to dust storms. Temperature swings from minus 100 degrees to positive 70 degrees Fahrenheit in cosmic radiation. It needs to extract water from Martian soil, which requires drilling or excavation equipment. It needs to process Martian atmosphere, which is thin and requires large compressors. It needs enormous amounts of electrical power, requiring either massive solar panel arrays or a nuclear reactor. And it needs to produce tens of tons of fuel, with essentially no maintenance, because the crew hasn't arrived yet. If anything goes wrong with the ISRU system, if it breaks down, if it doesn't produce enough fuel, if contamination ruins a batch, the crew is stranded. There's no backup plan. Earth can't send spare parts because the journey takes 6 to 9 months. By the time a problem is identified and a solution sent, years have passed. The crew either fixes it themselves with whatever materials they have available, or they don't go home. Second, ISRU requires time. The fuel production to process isn't instantaneous. Even with perfectly functioning equipment, producing 80,000 to 150,000 pounds of fuel takes months, possibly more than a year. This means the ISRU equipment needs to start operating as soon as it lands, long before the crew arrives. Mission planners typically assume that fuel production would begin at least 2 years before the crew launch and would continue operating through the entire surface stay. This extends the mission timeline even further and creates more opportunities for equipment failure. Third, ISRU has never been demonstrated at the scale required for human missions. Small-scale experiments have been proposed and tested in laboratories, but actually doing this on Mars with autonomous equipment producing mission-critical fuel is completely untested. The first crew to depend on ISRO for their return journey would be betting their lives that the system works as designed. If it doesn't, they die on Mars. No rescue mission is possible on reasonable timescales. Even if Earth immediately launched a rescue mission the moment a problem was detected, that rescue mission would take 6 to 9 months to arrive. More realistically, it would take years to prepare and launch a rescue mission. The stranded crew would die long before help arrived. This is fundamentally different from any previous human space mission. Apollo astronauts could abort and return to Earth within days if something went wrong. International Space Station crews can return to Earth within hours using Soyuz spacecraft. Mars crews have no abort option. Once the journey begins, they're committed. If ISRU fails, they're stranded. If life support fails, they die. If the habitat is damaged, they die. There's no rescue, no backup plan, no way home except the systems they brought with them. Now, let's talk about what happens to human bodies during the journey, because this might be the most insurmountable obstacle to a return mission. Space is hostile to human biology in ways that are difficult to overstate. Earth's environment, the gravity, the atmosphere, the magnetic field is calibrated perfectly for our biology because we evolved here. Every system in your body, your cardiovascular system, your skeletal system, your immune system, your vision, your balance, your cellular repair mechanisms, all of it developed over millions of years under Earth-specific conditions. When you remove those conditions, everything starts to break down. We've learned this from decades of space station research. Astronauts on the International Space Station experience measurable physical degradation after only a few weeks in microgravity. Bone density decreases at a rate of about 1 to 2% per month. This happens because bones are living tissue that constantly rebuilds itself in response to stress. When you stand, walk, or run on Earth, gravity creates stress on your bones and your body responds by maintaining bone density. In microgravity, there's no stress. So your body decides it doesn't need strong bones and starts breaking them down. The calcium from these bones is released into the bloodstream and eventually excreted. Astronauts on 6-month ISS missions lose about 10 to 15% of their bone density. This is comparable to the bone loss experienced by elderly people with osteoporosis. The bones become brittle, fracture risk increases dramatically, and the recovery process takes years. Some bone density never fully recovers even after returning to Earth. Muscle atrophy is equally severe. Without the constant work of supporting body weight against gravity, muscles weaken rapidly. Astronauts can lose up to 20% of their muscle mass during a 6-month mission, despite rigorous daily exercise. The exercise regimes on the ISS are intense. 2.5 hours per day of resistance training and cardiovascular work, and they only partially counteract the muscle loss. Cardiovascular changes are more subtle but equally concerning. On Earth, your heart works against gravity to pump blood to your brain. In microgravity, this isn't necessary, so the heart becomes weaker and more spherical instead of elongated. Blood pressure decreases. The cardiovascular system essentially deconditions itself. When astronauts return to Earth after long missions, they experience severe orthostatic intolerance, meaning they feel dizzy or faint when standing because their cardiovascular system can't adjust to pumping blood upward against gravity anymore. Some astronauts have fainted immediately after landing. Most need weeks of reconditioning before they can function normally. Vision problems affect about 60% of astronauts on long-duration missions. The mechanism isn't fully understood, but the leading theory is that in microgravity, fluid shifts toward the head because there's no gravity pulling it toward the feet. This increased fluid pressure in the skull appears to change the shape of the eyeball and may cause swelling of the optic nerve. Some astronauts have experienced permanent vision degradation after returning from space. The immune system weakens in space. Studies have shown that immune cells function less effectively in microgravity. Viruses that are normally dormant in your body, like the chickenpox virus or herpes viruses, can reactivate during spaceflight. Wound healing is slower, the risk of infection is higher, and there's evidence that radiation exposure, which we'll discuss momentarily, further suppresses immune function. Now take all of these problems: bone loss, muscle atrophy, cardiovascular deconditioning, vision changes, immune suppression, and extend them over 3 years instead of 6 months. A Mars mission crew would spend approximately 6 to 9 months in microgravity travelling to Mars, 2 years in Mars's gravity, which is only 38% of Earth's, then another 6 to 9 months in microgravity travelling back to Earth. Let's consider what this means for their bones. During the 18 months to 2 years spent in transit, bone loss continues at roughly 1 to 2% per month. Over 18 months, that's potentially 20 to 30% bone loss. Your skeleton becomes as fragile as an 80-year-old's. Simple movements that would normally be safe, getting out of bed, walking across a room, could result in fractures. Mars gravity is better than microgravity, but it's unclear if 38% of Earth's gravity is enough to stop bone loss. We've never studied humans in partial gravity environments. All our data comes from either Earth gravity or microgravity on the ISS. Mars gravity might slow bone loss or it might not. It's plausible that 38% gravity isn't enough stress to maintain bone density, meaning astronauts would continue losing bone throughout their entire stay on Mars. If that's true, by the time the return window opens after 2 years, the crew's skeletons would be so weakened that the return journey itself becomes life-threatening. Re-entry to Earth is violent. The spacecraft decelerates from orbital velocity about 17,500 miles per hour to 0 in a matter of minutes. Even with parachutes and heat shields, the crew experiences forces of several Gs. After 3 years of bone loss and muscle atrophy, could their bodies withstand these forces without fracturing? And even if they survive re-entry, what about recovery? Current ISS astronauts need months of physical therapy after 6-month missions to rebuild bone and muscle. After a 3-year Mars mission, recovery would take years, possibly the rest of their lives. Some degradation might be permanent. Bone density might never fully recover to pre-flight levels. Some astronauts might never walk normally again. There's also the question of whether bodies can even adapt back to Earth gravity after that long and reduced gravity environments. We have no data on this because no human has ever spent 3 years away from Earth gravity. It's possible that after a certain point, the human body adapts so completely to low gravity conditions that returning to Earth gravity is impossible. Your heart might not be able to pump blood against Earth's gravity anymore. Your bones might be too weak to support your weight. Your muscles might be incapable of moving your body. You might effectively be trapped by your own physiology. This is one of the darkest possibilities, that even if you successfully manufacture fuel on Mars, even if the spacecraft works perfectly, even if every system functions as designed, your body might no longer be capable of surviving the return to Earth. You'd arrive home only to discover that home is no longer habitable for you. Then there's radiation, which might be the most insidious threat of all. On Earth, we're protected from space radiation by 2 critical shields. Earth's magnetic field deflects charged particles from the solar wind and cosmic rays. Earth's atmosphere absorbs what the magnetic field doesn't catch. Together, these shields reduce our radiation exposure to safe levels. The average person on Earth receives about 0.3 rem of radiation exposure per year from natural sources. This is called background radiation, and it comes from cosmic rays that make it through the atmosphere. Radiation from rocks and soil, and natural radioactivity in our own bodies. On the International Space Station, which orbits within Earth's magnetic field and receives some protection from Earth itself, blocking radiation from below, astronauts receive about 15 to 20 REM per year. That's 50 to 60 times higher than on Earth's surface. A 6-month ISS mission exposes astronauts to about 7 to 10 REM total. This is considered acceptable risk. It increases cancer risks slightly but not dramatically. On a journey to Mars, there is no protection, no magnetic field, no atmosphere, nothing between you and space radiation except the walls of your spacecraft. These walls provide minimal shielding unless they're very thick, and thick walls mean more mass, which means more fuel required, which brings us back to the rocket equation problem. Practical spacecraft designs provide some shielding but not enough to reduce radiation to safe levels. During the 6 to 9 month journey to Mars, astronauts would be exposed to approximately 30 to 40 rem of radiation. During the 2-year stay on Mars, where there's a thin atmosphere providing minimal protection but no magnetic field, they'd receive approximately 40 to 60 REM depending on solar activity. During the return journey, another 30 to 40 REM total radiation exposure for a 3-year Mars mission is approximately 100 to 140 REM. This is well above the limits as established by NASA for career radiation exposure. NASA's limit for astronauts is based on age and gender, but generally caps lifetime exposure at about 100 to 200 REM depending on factors that affect cancer risk. A single Mars mission would consume most or all of an astronaut's allowable lifetime radiation exposure, but the numbers get worse if solar activity is considered. The Sun occasionally releases massive bursts of radiation called solar particle events or solar flares. These can deliver enormous radiation doses in short periods of time. A major solar particle event during a Mars mission could expose the crew to several hundred REM in a matter of hours. This would cause acute radiation sickness, vomiting, hemorrhaging, immune system collapse, and potentially death. Spacecraft can be designed with small shielded areas where crew can shelter during solar events, but these shelters add mass and don't protect against the constant background exposure from galactic cosmic rays. The health effects of this much radiation exposure are severe. Cancer risk increases dramatically, possibly by 20 to 30% over baseline. Cardiovascular damage occurs. Cataracts can develop. Central nervous system damage is possible, though less well understood. Studies on animals exposed to radiation similar to space radiation show cognitive impairment, memory loss, and changes in behavior. Some research suggests that space radiation might accelerate aging at the cellular level. And here's the truly disturbing part. We don't fully understand the long-term effects of space radiation because no human has ever been exposed to these levels. The Apollo astronauts who traveled to the moon left Earth's magnetic field protection, but only for about a week. ISS astronauts receive elevated radiation, but they're still partially protected by Earth's magnetic field. No human has spent 3 years in deep space exposed to unshielded radiation. We're extrapolating from animal studies, from short-duration human missions, and from mathematical models. The actual effects might be worse than predicted. There might be synergistic effects where radiation damage combines with bone loss and muscle atrophy and immune suppression to create problems we haven't anticipated. The human body might simply not be designed to survive 3 years in space. Evolution shaped us for Earth. Space is not Earth. Every day in space, every month, every year is fundamentally damaging to human biology. We can mitigate some of the damage with exercise, with medication, with careful mission planning, but we can't eliminate it. And after 3 years, the accumulated damage might be irreversible. Let's talk about the practicalities of life support and resource management, because this is where the differences between a one-way mission and a round-trip mission become stark. Every human needs certain things to survive: air, water, food, temperature regulation, waste disposal. On Earth, these are provided by planetary systems. The atmosphere provides air. The hydrosphere provides water through rain and rivers and oceans. The biosphere provides food through agriculture. The climate system regulates temperature. We don't think about these things because they're automatic, part of the background of existence. In space, nothing is automatic. Every breath of air must be generated or recycled. Every drop of water must be brought or reclaimed from waste. Every meal must be packed and preserved or grown in artificial environments. Temperature control requires active systems. Waste must be processed and disposed of or recycled. For short missions like Apollo or even ISS missions, you can bring supplies from Earth. Apollo astronauts brought air tanks, water tanks, and packaged food. ISS crews receive regular resupply missions from Earth every few months, bringing fresh food, water, equipment, and spare parts. If something breaks on the ISS, a replacement can be sent on the next resupply flight. If supplies run low, more can be delivered. The ISS is supported by Earth. It's an extension of Earth infrastructure, not an independent settlement. A Mars mission cannot work this way. The distances are too great. Communication alone takes between 4 and 24 minutes each way, depending on where Earth and Mars are in their orbits. If something breaks, you can't call Earth and get advice in real time. By the time your distress message reaches Earth and a response comes back, between 8 and 48 minutes have passed. If the problem is urgent, minutes matter, and waiting nearly an hour for advice could be fatal. Resupply missions are essentially impossible on useful timescales. If the crew runs out of critical supplies, if a key system fails, Earth can't send help that would arrive in time. A resupply mission would take 6 to 9 months to reach Mars. The crew would be dead long before it arrived. This means a Mars mission must be completely self-sufficient. The habitat, the life support systems, the food production, all of it must function for the entire duration of the mission without external support. This is an extraordinarily difficult engineering challenge. The ISS life support system is one of the most complex machines ever built. It recycles air by removing carbon dioxide and using electrolysis to split water into oxygen and hydrogen. The oxygen is released into the cabin air. The hydrogen is either vented or combined with carbon dioxide to produce water through the Sabatier reaction. The system recycles about 90% of water, recovering it from humidity in the air, from urine, and from other waste streams. Achieving higher recycling rates would require even more complex systems. This system works on the ISS, but it's not fully closed. The ISS still requires regular shipments of water from Earth because the recycling isn't perfect. Small amounts of water are lost and must be replaced. The system also requires regular maintenance, replacement parts, and repairs. On Mars, you can't rely on regular shipments from Earth. The life support system must be truly closed-loop, recycling nearly 100% of air and water. Any losses must be made up from local resources on Mars. This means extracting water from Martian soil, which adds complexity and energy requirements. Food is an even bigger challenge. Humans need about 2,000 to 2,500 calories per day, depending on activity level. For a crew of 4 spending 3 years on Mars, that's approximately 9 million calories total. Packaged food has limited shelf life. Most freeze-dried or dehydrated foods remain edible for 5 to 10 years under ideal storage conditions, but those conditions include stable temperature, low humidity, and protection from radiation. Mars surface temperatures swing wildly, radiation is constant. Storage containers would need to be heavily insulated and shielded, adding mass. The alternative is growing food on Mars. This is theoretically possible. Plants can grow in Martian regolith if it's supplemented with nutrients and organics. LED lighting can provide the necessary wavelengths for photosynthesis. Water can be recycled from plant transpiration and human waste. But growing enough food to sustain a crew requires significant infrastructure. You need a pressurized greenhouse with temperature control. You need thousands of watts of electrical power for lighting, far more than needed for basic life support. You need to deal with crop failures, diseases, pests, and contamination. You need to store seeds and maintain genetic diversity. And you need expertise. Someone in the crew needs to understand agriculture, plant biology, and how to troubleshoot problems when crops fail. Experiments on the ISS have grown small amounts of lettuce and radishes, but these are tiny proof-of-concept demonstrations. Growing all the food for a crew for years is orders of magnitude more difficult. If the food production system fails, the crew starves. There's no backup. Earth can't send emergency rations in time. The crew either fixes the problem themselves or they die. Every system on Mars must be designed with this reality in mind. There are no second chances, no rescue missions, no emergency supplies from Earth. Redundancy is critical. Every vital system needs backups and backups for the backups, but redundancy adds mass and complexity, which increases costs and failure modes. It's a brutal optimization problem with human lives hanging in the balance. Now let's confront the economic reality, because this is where the arguments for one-way missions become overwhelming. Space missions are expensive. The Apollo program cost approximately $150 billion in today's currency. That was for 6 successful lunar landings, 12 humans walking on the moon, and a total of about 75 person-days of lunar surface time. The cost per person per day was about $2 billion. The International Space Station has cost approximately $150 billion to build and operate over its lifetime, spread among participating countries. For that cost, it has supported continuous human presence in space for over 20 years with crews of 3 to 7 people. The cost per person per year is roughly $1 billion to $2 billion. These are staggering sums, but they're for missions relatively close to Earth with robust support infrastructure. Mars missions are far more expensive. Estimates for a crewed Mars mission with return capability range from $100 billion on the very low end to over $500 billion for more realistic designs. SpaceX claims they can do it cheaper, perhaps $50 billion. But these estimates assume massive technological development that hasn't happened yet, like reliable SRU, reusable spacecraft that can make multiple round trips, and launch costs that are a fraction of current prices. Even if SpaceX's optimistic estimates are correct, $50 billion is an enormous sum. That's roughly the entire annual budget of NASA. Spending that much money on a single mission requires justification. What's the return on investment? What scientific discoveries or economic benefits justify $50 to $500 billion? And here's where the calculation changes dramatically. A one-way mission costs a fraction of a round-trip mission. If you don't need to bring fuel for the return journey, your spacecraft can be much smaller and lighter. If you don't need to design for re-entry to Earth, you can simplify the vehicle. If you're establishing a permanent settlement rather than a temporary visit, you can send supplies and equipment over multiple missions, spreading the cost over time. The cost difference between a one-way mission and a round-trip mission is roughly a factor of 5 to 10. A one-way mission might cost $10 to $50 billion. A round-trip mission costs $50 to $500 billion. For the cost of sending one crew to Mars and bringing them back, you could send 5 to 10 crews one way. You could establish a permanent base with a population large enough to sustain itself to conduct meaningful research to begin resource extraction and development. From a purely economic perspective, one-way missions make far more sense. You get more people to Mars for the same cost. You establish a permanent presence rather than a symbolic flag planting. You begin the long process of making humanity a multi-planet species. The counter-argument is that sending people on one-way missions is morally questionable. You're asking people to accept exile, to say goodbye to Earth forever, to give up any possibility of returning home. This seems cruel, perhaps unconscionable, but is it? Throughout history, humans have undertaken one-way journeys. The Polynesian voyagers who settled the Pacific Islands left their homes knowing they could never return. The European colonists who sailed to the Americas in the 15th and 16th centuries undertook journeys that typically lasted months, cost a significant portion of their wealth, and offered no guarantee of survival. Most of them never returned to Europe, not because return was physically impossible, but because the cost and difficulty made it impractical. They left their homes, their families, their entire world behind to start new lives in unknown lands. Many died during the journey or shortly after arrival. Those who survived built new societies. Their descendants became Americans, Australians, Canadians, populations distinct from their European ancestors. The Polynesian and European colonizations were one-way journeys by practical necessity. Mars colonization would be one-way by physical necessity. The physics of interplanetary travel make return trips exponentially more difficult than one-way trips. Given this reality, perhaps we should stop pretending Mars missions are like Apollo. They're not exploration missions, they're colonization missions. The first humans on Mars will be colonists, not astronauts. They'll be leaving Earth permanently to establish humanity's first foothold on another planet. This is a different kind of courage than Apollo required. Apollo astronauts were heroes who risked their lives but expected to return. Mars colonists will be pioneers who accept exile, who trade Earth for Mars, who choose a life on an alien world knowing they'll never see home again. Some people will volunteer for this. Not everyone. Probably not most people, but some. There are always those who crave adventure, who want to be part of something larger than themselves, who are willing to sacrifice comfort and safety for meaning and purpose. These are the people who will go to Mars. And from an economic perspective, supporting them makes more sense as a permanent colony than as temporary visitors. Spend the money once to establish infrastructure that lasts decades rather than spending even more money to bring people back. Build habitats designed for long-term occupation, not minimal survival shelters. Send equipment for resource extraction, manufacturing and construction, not just scientific instruments. Create the foundation for a self-sustaining settlement that will eventually not need Earth support. This is the only economically rational approach to Mars, given the physics and costs involved. The psychological reality of a one-way mission is complex and often overlooked. When you board a spacecraft to Mars knowing you'll never return, you're not just leaving Earth physically, you're leaving it psychologically. You're severing your connection to everything familiar, your family, your friends, your culture, the sky you grew up under, the gravity your body knows, all of it is gone forever. This is a form of death, in some sense. The person you were on Earth can never exist again because the environment that shaped you no longer exists in your life. You have to become someone new, someone adapted to Mars, someone who thinks of red skies and pink sunsets as normal, someone who instinctively adjusts to low gravity, someone whose entire frame of reference is this alien world. Studies have been done on the psychology of extreme isolation and long-duration missions. Antarctic research stations provide some analogies. Crews spending winters at Antarctic bases experience psychological challenges from isolation, confinement, and the extreme environment. But they know the winter will end. They know a ship or plane will come to take them home. This knowledge, even if they never consciously think about it, provides psychological stability. There's an end point, a return to normally. Mars colonists won't have that. There's no end point where things return to normal. Mars is normal now. Earth is the memory, the dream, the place that exists only in videos and photographs and stories. Some people will handle this well. Humans are remarkably adaptable. We adjust to new environments, form new communities, find meaning in new circumstances. The Mars colony would develop its own culture, its own traditions, its own sense of identity distinct from Earth. Within a generation, children born on Mars would consider Mars home. Earth would be the exotic faraway place where their parents came from. But the transition period, the first years after arrival, when colonists are still psychologically tied to Earth, but physically cut off from it, will be difficult. Depression, anxiety, interpersonal conflicts, all the psychological challenges of isolated groups will be amplified by the permanence of the situation. There's no quitting, no going home, no escape. Conflict resolution becomes critical because you can't remove someone from the group without killing them. Mission planners will need to screen candidates carefully for psychological resilience, but they'll also need to prepare for the reality that some people won't adapt well. What happens when someone has a psychological breakdown on Mars? What happens when someone decides they made a mistake? They want to go home, and you have to explain that home no longer exists for them. These aren't theoretical questions. They will happen, and the colony will need systems for dealing with them. Support structures, mental health resources, and cultural norms that help people cope with the existential weight of permanent exile. The Mars One project, which proposed sending colonists on a one-way mission to Mars, received over 200,000 applications when they opened recruitment. 200,000 people volunteered to leave Earth forever. Now, Mars One turned out to be a poorly planned venture that collapsed before sending anyone anywhere. But the application numbers are significant. They demonstrate that there are people willing to make this choice. People who find the prospect of being Mars pioneers more compelling than remaining on Earth. Some applied for adventure, some for scientific passion, some because they felt disconnected from Earth society and wanted a fresh start. Some because they wanted to be part of history. The motivations varied, but the willingness was real. These are the people who will colonize Mars. Not everyone, not most people, but a self-selected group who have made peace with never returning. And in some ways, knowing it's one way might make the psychological adjustment easier. There's no false hope of return, no longing for something unattainable. You accept from the beginning that Mars is home now, and you invest fully in making it work. You don't spend years dreaming about Earth and counting down to a return date that might never come. You commit completely to your new world. There's another angle to consider, which is the timeline trap. Every 26 months, a new launch window opens. Technology improves continuously. Each year, rockets become more capable. Life support systems become more reliable. Our SRU technology becomes more proven. If you're planning a round-trip mission, you face a difficult choice. Launch in the current window with current technology, or wait 26 months for the next window when technology will be better. And when that next window comes, you face the same choice. The technology will be even better in another 26 months. Waiting always seems rational because the next mission will always be safer, cheaper, more capable. This creates a perverse incentive to delay indefinitely. Why risk lives with marginal technology when waiting 2 more years gives you better odds? But waiting means no mission happens, decades pass with planning and development, but no actual Mars landings. This is essentially what's happened since the Apollo era ended. We've been planning Mars missions for 50 years. Detailed designs exist. Technologies have been developed, but we've never committed to actually going because there's always a reason to wait to develop better systems to reduce risk further. If Mars missions are framed as round-trip missions, this pattern will continue. The bar for safety and reliability is so high that achieving it requires technology that doesn't exist yet. And by the time that technology exists, new capabilities will be on the horizon that could make missions even safer. The waiting never ends. One-way missions break this cycle. The risk threshold is different. You're not trying to bring people back safely. You're trying to establish a viable settlement. The question isn't whether the mission is safe enough for a round trip. It's whether colonists can survive and thrive on Mars. That's still a high bar, but it's achievable with current technology or near-term developments. Life support systems that can sustain people for years exist. Habitats that can protect against radiation and provide livable space can be built. ISRU systems are being tested. The technology to land people on Mars and keep them alive exists or will exist within a decade. It's not perfect, it's not as safe as we'd like, but it's sufficient for colonization. Framing Mars missions as colonization rather than exploration changes the risk calculation. Colonists accept higher risk than astronauts because they're investing in something permanent. They're building a future, not just collecting data. And because the mission is permanent, there's less pressure to perfect every system before launch. The colony can be improved over time with subsequent missions bringing better equipment, more supplies, new colonists with needed skills. It's an iterative process rather than a single high-stakes round trip. This approach is more likely to actually result in humans on Mars within our lifetimes. Waiting for the perfect round-trip mission means waiting forever. Accepting that the first missions are one way means accepting that Mars colonization can begin now, with current technology and realistic budgets. Let me bring this back to the fundamental physics and biology we've discussed. A human body in space or on Mars for 3 years undergoes changes that might make return to Earth impossible. Bone loss, muscle atrophy, cardiovascular changes, radiation damage. All of these compound over time. There may be a point of no return, a threshold beyond which the human body is too adapted to low gravity to survive Earth's environment. We don't know where that threshold is because we've never tested it. The longest single spaceflight was 437 days by Russian cosmonaut Valery Polyakov on the Mir space station. He returned to Earth, though he needed extensive rehabilitation, but 437 days is about 15 months. A Mars mission is 3 years more than twice as long. The accumulated effects might be fundamentally different. Children born on Mars, if colonization proceeds to that stage, will never be able to visit Earth. A child who grows from Earth in Mars's 38% gravity will develop bones and muscles adapted to that environment. Their cardiovascular system will develop for pumping blood in low gravity. Their entire physiology will be Martian, not earthly. If they travel to Earth, the higher gravity would be crushing. Their bones might fracture under their own weight. Their hearts might not be able to pump blood effectively against the higher gravity. They'd be disabled or dead within hours or days of arrival. Martian humans, if they emerge, will be a separate population from Earth. Humans unable to cross the gap between worlds. This sounds like science fiction, but it's straightforward biology. Bodies adapt to their environment. Humans who spend their entire lives in low gravity will have bodies designed for low gravity. Earth will be as alien to them as Mars is to us. This has profound implications for the concept of return. Even if technology advances to make return missions economically feasible, even if ISRU becomes reliable and efficient, there may be a biological barrier that prevents people from returning. The first Mars colonists might physically adapt to Mars in ways that make them unable to survive Earth. Their mission becomes one way, not by choice or by technology limitations, but by biology. Their bodies close the door behind them. And perhaps that's appropriate. Evolution is adaptation to environment. Humans evolved on Earth, adapted to Earth's specific conditions over millions of years. If we are going to become a multi-planet species, we'll need to adapt to new environments. Mars humans, if the colony survives long enough, will eventually become distinct from Earth humans. Not a different species, at least not for thousands of generations, but a different population with different physical characteristics. Taller, perhaps because Mars gravity doesn't compress the spine as much. Different muscle distribution adapted for moving efficiently in low gravity. Different cardiovascular systems, different bone density over very long time scales. Measurable evolutionary divergence. This is what colonization means. Not just moving to a new place, but becoming something new, something adapted to that place. The first colonists will be Earth humans trying to survive on Mars. Their children will be Martians who remember Earth as a story. Their grandchildren will be fully Martian, shaped by the red planet, thinking of it as home in a way no Earth human ever could. Let's address the elephant in the room. Is it ethical to send people on one-way missions? Is it moral to ask people to accept permanent exile? Is it justifiable to spend billions of dollars to establish a Mars colony when that money could address problems on Earth? These are legitimate questions and they don't have simple answers. The ethical framework depends on how you view human expansion into space. If you see it as a luxury, a vanity project for wealthy nations or individuals, then no. Spending hundreds of billions on Mars colonization is not justifiable when people on Earth are suffering from poverty, disease, and lack of basic resources. But if you see it as an investment in humanity's long-term survival, as insurance against existential risks that could wipe out Earth-based civilization, then the calculation changes. Earth faces real risks. Asteroid impacts, though rare, are possible and would be devastating if one hit a populated area. Supervolcano eruptions could trigger global climate catastrophes. Nuclear war remains a possibility. As long as nuclear weapons exist, pandemics could potentially kill millions or billions. Climate change is already altering Earth's environment in ways that will cause suffering and displacement. Human-caused ecological collapse could make parts of Earth uninhabitable. And beyond these near-term risks, there are longer-term inevitabilities. The sun is slowly brightening as it ages. In about 1 billion years, Earth will become too hot for life. In about 5 billion years, the sun will expand into a red giant and consume Earth entirely. These timescales seem absurdly long from a human perspective, but they're certainties. Earth has an expiration date. If humanity is confined to Earth, humanity has an expiration date. Establishing self-sufficient settlements on other worlds is the only way to ensure long-term survival. Beyond Earth's lifespan, Mars won't save everyone. A Mars colony, even a successful one, will probably never support more than a few thousand or tens of thousands of people for many decades, possibly centuries. It's not a solution to Earth's problems. It's not an escape for the masses, but it's a backup, a second location where human civilization can continue if something catastrophic happens to Earth. From this perspective, the cost of Mars colonization is the price of insurance against extinction. Is that worth $50 billion or $100 billion? Many would argue yes. Governments spend comparable amounts on military defense against threats that may never materialize. Spending a fraction of global GDP to establish humanity's first foothold on another world seems like a reasonable investment in our long-term future. The ethical question of asking individuals to accept permanent exile is more nuanced. In one sense, it's no different from asking soldiers to risk death in war, or asking test pilots to fly experimental aircraft, or asking mountain climbers to attempt Everest. We routinely accept that some people will voluntarily take on enormous risks for causes they believe in. If someone fully understands the risks and consequences of a one-way Mars mission and volunteers anyway, is it unethical to allow them to go? They're adults making informed decisions about their own lives. The key is informed consent. Candidates must understand completely what they're agreeing to. Not just the technical risks, but the psychological reality of permanent separation from Earth, the physical toll on their bodies, the possibility that life on Mars will be harder and shorter than life on Earth, the knowledge that if something goes wrong, no rescue is coming. If they understand all of this and still volunteer, then allowing them to go respects their autonomy and their choice to participate in something historically significant. The alternative is paternalism, deciding that we know better than they do what's good for them. Some people will make the calculation that being part of the first Mars colony, contributing to humanity's expansion into space. Living on the frontier of human achievement is worth the cost of never returning to Earth. That's a valid choice. Not everyone will make it. Probably not most people. But for those who do, we should respect their decision. Let me bring all of this together. We've covered the distance problem, the orbital mechanics that require waiting 2 years on Mars before a return window opens. We've covered the fuel problem, the exponential relationship between velocity and fuel mass that makes return missions require exponentially more resources than one-way missions. We've covered ISRU as a potential solution and all the uncertainties and risks it introduces. We've covered the physical toll on human bodies, bone loss and muscle atrophy, and radiation exposure that accumulates over 3 years to potentially irreversible levels. We've covered the life support and resource challenges, the need for completely closed-loop systems with no possibility of resupply from Earth. We've covered the economic reality that one-way missions are 5 to 10 times cheaper than round-trip missions. We've covered the psychological aspects of permanent exile and the self-selection of people willing to become Mars colonists. We've covered the timeline trap where waiting for better technology means never actually going. And we've covered the biological possibility that bodies adapted to Mars might not be able to return to Earth even if technology allows it. All of these factors point in the same direction. Mars missions, at least the first ones, will be one way. Not because we want them to be, not because we're cruel or short-sighted, but because the physics, biology and economics, nomics, make one-way missions feasible and round-trip missions extraordinarily difficult. This doesn't mean return missions are impossible forever. Technology improves. Maybe in 50 years or a century, we'll have developed propulsion systems that make the fuel problem manageable. Maybe we'll understand human physiology and low gravity well enough to develop countermeasures that prevent the deterioration we see now. Maybe there will be regular traffic between Earth and Mars with ships carrying cargo and people back and forth. But that's the far future if it happens at all. The first Mars missions will be one way. The first colonists will be pioneers who never return. And maybe that's appropriate. Throughout history, pioneers have left their homes to settle new lands. They've crossed oceans, traversed continents, endured hardships that killed many of them. The ones who survived built new societies in new places. Their sacrifice, their courage, their willingness to leave everything behind created the world we live in today. Let me get more specific about what the actual mission profile would look like for these first colonists, because understanding the details makes the reality even clearer. The mission would likely begin with cargo flights. Multiple unmanned missions would launch during several launch windows before the crew ever leaves Earth. These cargo missions would carry the habitat modules, the life support equipment, the ISRU systems for fuel production, solar panels or nuclear reactors for power, food supplies, medical equipment, tools, spare parts, everything needed to survive. This pre-deployment phase might take 4 to 6 years, 2 to 3 launch windows, delivering perhaps 80 to 100 tons of cargo to Mars' surface. Each cargo mission would take 6 to 9 months to travel to Mars, then spend months or years operating autonomously on the surface, deploying equipment, setting up systems, beginning fuel production. By the time the crew launches, there should theoretically be a functioning base waiting for them. Habitats inflated and pressurized, life support systems running, power generation operational, fuel tanks filling for potential future use. The crew would launch knowing their survival depends entirely on equipment that's been sitting on Mars for years, operating without human supervision. If anything critical has failed during that time, they're flying toward their death. They won't know for certain until they arrive. The journey itself would be brutal. 6 to 9 months in a spacecraft likely smaller than a large RV. A crew of 4 to 6 people, the minimum needed for safety and skill redundancy, living in extremely confined spaces. Every cubic meter would be precious, filled with supplies, equipment, or crew stations. Privacy would be essentially non-existent. You'd be seeing the same faces, hearing the same voices, smelling the same smells every single day for months. The psychological research on Antarctic stations and submarine crews shows that even well-adjusted people experience significant stress from prolonged confinement with the same small group. Interpersonal conflicts arise over trivial things. Someone's chewing habits become unbearable. Someone's conversation patterns grate on your nerves. Minor annoyances magnify into major frustrations because there's no escape, no way to get away and decompress. On Earth, if you have a fight with your roommate, you can leave, go for a walk, visit a friend, get some space. In a Mars transit vehicle, there's nowhere to go. The entire habitable universe is a few rooms, and the same people are in all of them. Mission planners will screen for psychological compatibility and resilience, but they can't eliminate these stresses, only mitigate them. The crew will need strict protocols for conflict resolution, designated private spaces, schedules that give people time alone or in different combinations to avoid constant exposure to the same group dynamics. And they'll need to maintain these protocols for 6 to 9 months, knowing that this is just the beginning. The real challenge starts after they land. Landing on Mars is dangerous. The atmosphere is thick enough to require heat shields and generate enormous heat during entry, but too thin for parachutes alone to slow you sufficiently. Every successful Mars landing has used a combination of heat shields, parachutes, and retro rockets, and even with all these systems, the final moments are terrifying. The Mars Science Laboratory mission that landed the Curiosity rover used a sky crane system where a rocket-powered platform lowered the rover on cables for the last few meters. It worked, but it was described by engineers as 7 minutes of terror. Every step had to work perfectly with no possibility of human intervention, because the communication delay meant Earth wouldn't even know if landing succeeded until 14 minutes after it was over. A crewed landing would be even more complex. The vehicle would be larger and heavier, requiring more propellant for the final descent. The crew would be awake and aware through the whole process, knowing their lives depend on systems functioning flawlessly during hypersonic entry and supersonic deceleration. Any failure means death. If the heat shield cracks, they burn up. If the parachutes don't deploy, they impact at terminal velocity, If the retro rockets fail, they crash. There are no second chances, no abort modes. Once entry begins, you're committed to landing or dying. Assuming successful landing, the crew would then begin the most critical phase, checking all the pre-deployed systems. Did the habitat survive the years of waiting? Are they still pressurized, or did micrometeorite impacts puncture them? Is the life support functioning, or did a component fail? Is there power, or did the solar panels get covered in dust? Is there water, or did the extraction system malfunction? Is there food, or did the storage containers fail? Every system critical to survival would need to be verified, and if anything major has failed, the crew would have to repair it quickly. They'd have limited supplies carried in their landing vehicle, enough for perhaps a few weeks of independent survival. If they can't get the main habitat systems running within that window, they die. No rescue is possible. Earth doesn't even know they've landed yet because of the communication delay. By the time Earth receives the landing confirmation and can assess any problems, hours have passed. By the time engineers on Earth can analyze the situation and send advice, more hours pass. Critical decisions need to be made on Mars by the crew with whatever resources they have immediately available. This is where the nature of one-way missions becomes stark-kest. Every problem is potentially fatal and every solution must be improvised from available resources. You can't wait for replacement parts from Earth. You can't consult with experts in real time. You can't evacuate if conditions become too dangerous. You solve the problem with what you have, or you die. This requires a specific kind of crew, not specialists who are expert in one narrow field, but generalists who understand multiple systems and can improvise solutions. Not people who follow procedures perfectly, but people who can assess novel problems and devise novel solutions. Not people who need extensive support infrastructure, but people who are comfortable with self-reliance and acceptable risk. The selection process for Mars colonists would be fundamentally different from astronaut selection for ISS missions. ISS astronauts are selected for technical competence, ability to follow procedures, and ability to work within a highly structured support system. They're experts who do exactly what mission control tells them to do. Mars colonists would need to be selected for adaptability, creativity under pressure, psychological resilience, and ability to function independently. They'd be more like frontier settlers than astronauts, expected to solve problems without extensive guidance, to take calculated risks when necessary, to accept uncertainty and danger as normal conditions of life. And they'd need to maintain this mindset not for weeks or months, but for years, possibly for the rest of their lives. The daily reality of life on Mars would be harsh in ways that are difficult for Earth-based people to appreciate. Every breath of air is recycled, filtered through mechanical systems that must function continuously. Every drop of water has been through your body or someone else's body multiple times, extracted from urine and sweat and exhaled breath, purified and reused in an endless cycle. Every meal comes from food you grow in Martian soil, supplemented with stored supplies, knowing that a crop failure means hunger or starvation. You live in a pressurized bubble surrounded by an environment that's trying to kill you. Go outside without a pressure suit and you'd be dead in seconds. The thin atmosphere would cause your blood to boil. The cold would freeze your tissues. The lack of oxygen would asphyxiate you, even if you could somehow survive the pressure and temperature. Every EVA, every trip outside the habitat to repair equipment or collect samples or tend to external systems is a life or death proposition. Your suit is your life support, and if it fails, you have minutes at most to get back inside. The psychological weight of this is hard to overstate. On Earth, if you want to go outside, you open a door and step out. On Mars, going outside requires an hour of preparation, checking your suit system, verifying oxygen levels, confirming pressure seals, going through depressurization cycles. And once you're out there, you're intensely aware that a small puncture, a seal failure, a system malfunction means death. You move carefully, avoid sharp rocks, double-check every action. The Mars environment never becomes safe or comfortable. It's always hostile, always dangerous, always requiring vigilance. Over time, this creates psychological stress that's difficult to measure, but impossible to ignore. Humans aren't designed for constant vigilance. We're designed to relax when safe, to let our guard down, to exist without constant awareness of environmental threats. Mars doesn't allow that. You're never safe, only temporarily protected by technology that could fail. The social dynamics of a small isolated colony are another challenge that gets insufficient attention in most Mars mission planning. A crew of 4 to 6 people is large enough to have some social diversity, but small enough that interpersonal conflicts can become debilitating. Everyone knows everything about everyone else. There are no secrets, no privacy, no way to avoid people you don't get along with. In a larger community, if you have conflicts with someone, you can minimize contact, interact with other people, dilute the relationship through a broader social network. In a group of 6 people on Mars, you can't avoid anyone. You see them every day, work with them, depend on them for survival. If serious interpersonal conflicts develop, there's no mechanism for resolution except the group working it out internally. You can't fire someone or ask them to leave because there's nowhere for them to go. You can't separate people into different living areas because space is limited and everyone needs access to critical systems. The group has to function as a cohesive unit or the mission fails. This places enormous pressure on social cohesion. Small resentments can't be allowed to fester into larger conflicts. Personality clashes must be managed proactively. Everyone needs to maintain professional relationships even when personal relationships are strained. This is exhausting. It's emotionally draining to constantly manage your own emotions and reactions. To be diplomatic and considerate even when you're frustrated or angry. To maintain group harmony when you'd rather withdraw or express your feelings openly. Research on small isolated groups shows that social conflicts are one of the most common sources of psychological stress, often more impactful than physical danger or harsh conditions. People can tolerate terrible environments if they have good social support. People struggle with good environments if social dynamics are toxic. A Mars colony with interpersonal conflicts would be a nightmare scenario. The crew would still have to work together, still have to trust each other in life-threatening situations, still have to live in close proximity, all while managing underlying tensions and resentments. This is why psychological screening for Mars missions would need to emphasize not just individual resilience, but social compatibility. The crew needs to be people who genuinely get along, who have compatible communication styles, who can resolve conflicts constructively, who can maintain good relationships under stress, and even with perfect screening, problems will arise. Humans are complex and relationships change over time. People who get along well initially might develop conflicts after months or years of constant contact. The mission would need built-in mechanisms for managing this, possibly including trained mediators within the crew, protocols for conflict resolution, and cultural norms that prioritize group cohesion over individual preferences. Let me also address the children question more directly, because if this is truly a permanent colony, eventually there will be children born on Mars. This raises profound ethical and biological questions. A child conceived and born on Mars would develop in 38% of Earth's gravity. Their bones would form under different stress conditions. Their muscles would develop for moving in low gravity. Their cardiovascular system would adapt to pumping blood against less gravitational resistance. By the time they're adults, their physiology would be fundamentally Martian. Would such a person be able to visit Earth? Almost certainly not. The transition to Earth gravity would likely be physically devastating. Their bones might not support their own weight. Their heart might not be able to pump blood effectively against higher gravity. They might experience constant fatigue, muscle weakness, and orthostatic problems. In extreme cases, the transition could be fatal. Their cardiovascular system might fail under the increased demands. They'd be trapped on Mars not by lack of technology, but by their own biology. This creates an ethical dilemma. Is it acceptable to have children knowing they'll never be able to leave Mars? That they'll be born into permanent exile not by choice but by circumstance of birth? Some would argue this is unconscionable, that we shouldn't create humans who are fundamentally limited in where they can exist. Others would argue that location of birth has always imposed limitations, and being born on Mars is no different from being born in any specific location on Earth. You can't choose where you're born, and everyone grows up adapted to their local environment. The difference is degree, not kind, but there's also the question of informing children about Earth. How do you raise a child on Mars? Do you teach them about Earth? Show them videos of blue skies and oceans and forests? Do you tell them about the 7 billion people living there? About the diversity of cultures and environments? Or do you minimize Earth's importance? Focus on Mars as home, try to prevent homesickness or longing for a place they can never visit. Both approaches have problems. If you emphasize Earth, you risk creating children who feel cheated, who resent being born on Mars instead of Earth, who long for a home they can never experience. If you de-emphasize Earth, you risk creating cultural isolation, losing connection to human history and civilization, developing a Mars culture that has no tie to its origins. The balance would be delicate, and different families would probably handle it differently. creating potential social divisions within the colony. And there's the practical question of genetic diversity. A colony of 4 to 6 initial settlers doesn't have enough genetic diversity to sustain a population long term. Inbreeding would become a problem within a few generations. The colony would need regular influxes of new settlers to maintain genetic diversity, which means continued support from Earth. A truly self-sufficient Mars colony might require a population of several hundred people to maintain genetic diversity over many generations. That's far beyond the scale of initial missions. It would take decades of continuous missions, hundreds of colonists volunteering for one-way trips to build a population large enough to be genetically sustainable. This long-term commitment is part of what makes Mars colonization so challenging. It's not a single mission or even a series of missions. It's a sustained multi-generational effort requiring consistent political will, funding, and volunteers over many decades. Any interruption, any loss of political support on Earth, any economic crisis that prevents continued missions could doom the colony. A small Mars settlement can't survive indefinitely without resupply from Earth. They need genetic diversity. They need specialized equipment that they can't manufacture. They need cultural connection to prevent isolation and stagnation. Only once a colony reaches the certain critical size, probably several thousand people with diverse skills and substantial manufacturing capability, could it potentially survive without Earth's support. That threshold is many decades away under even optimistic scenarios. The resource extraction and manufacturing challenges are also worth exploring in more detail. Mars has resources, but exploiting them requires industrial capability that doesn't exist initially. Water ice exists in Martian soil, but extracting it requires excavation equipment, heating systems, and purification processes. Iron is abundant in Martian regolith, but smelting iron requires temperatures of over 2,700 degrees Fahrenheit and substantial energy input. Manufacturing anything complex, electronics, precision parts, medical supplies, requires industrial infrastructure that would take years to establish. Initially, the colony would be completely dependent on imports from Earth. Every tool, every spare part, every piece of equipment comes from Earth and takes 6 to 9 months to arrive. If something breaks and there's no spare, you either fabricate a replacement from available materials, which requires creativity and luck, or you do without. This creates a constant tension between using equipment and preserving it. Every use of a tool is potential wear that might lead to failure. Every system that operates is accumulating damage that will eventually require repair or replacement. The colony would need to be obsessively careful about maintenance, about rationing the use of irreplaceable equipment, about improvising solutions that don't require Earth imports. Over time, as the colony grows and subsequent missions deliver more industrial equipment, local manufacturing capability would increase. Basic metal working, creating simple tools and parts from Martian iron, 3D printing of plastic components from recycled materials or locally manufactured feedstock, glass production from Martian silicate for windows, optics, and laboratory equipment, eventually more complex manufacturing, electronics assembly, chemical synthesis, pharmaceutical production. But this progression would take decades, and even then the colony would remain dependent on Earth for high-complexity items. You can't easily manufacture computer chips or advanced medical equipment without extensive industrial infrastructure. A Mars colony wouldn't achieve Earth-level manufacturing capability for a very long time, possibly centuries. This long-term dependence on Earth's supply lines is another reason why Mars missions are better framed as colonization rather than independence. The colonists aren't establishing a fully independent society. They're establishing an outpost that remains connected to and dependent on Earth civilization even while being physically separated from it. It's more like remote research stations in Antarctica than like the European colonization of the Americas. Antarctic stations are permanently occupied, but they're supplied by their home nations. They don't try to be self-sufficient because the environment doesn't support it. Mars colonies would be similar for many decades, permanently occupied but supplied by Earth because full self-sufficiency isn't achievable with small populations. The communication delay deserves more exploration too because it affects every aspect of colony life in ways that are easy to underestimate. At minimum, when Mars and Earth are closest, radio signals take about 4 minutes to travel between planets. At maximum distance, it's about 24 minutes. This means every communication with Earth has a minimum round-trip time of 8 to 48 minutes. You ask a question, wait 4 to 24 minutes for your message to reach Earth. Wait for someone to compose a response. Wait another 4 to 24 minutes for the response to reach you. Simple conversations that would take seconds on Earth takes hours on Mars. This fundamentally changes the nature of communication. You can't have real-time conversations with family or friends on Earth. You can't call home when you're feeling lonely and have someone talk to you immediately. You exchange messages, but with such long delays that each exchange feels less like conversation and more like letter writing. This delay also affects technical support. If equipment fails and you need advice from engineers on Earth, you send a description of the problem, wait for them to analyze it and respond, then receive their advice hours later. By that time, the situation might have changed. You might have already solved the problem, or it might have gotten worse, or new complications might have arisen. The delay makes real-time technical support impossible. You have to be self-sufficient, able to diagnose and solve problems with minimal external input. It affects mission operations too. On the ISS, Mission Control can monitor systems in real time and alert the crew to problems immediately. On Mars, Mission Control sees data that's 4 to 24 minutes old. By the time they notice a problem and send a warning, the problem might have already caused damage or been solved by the crew. The crew has to monitor their own systems, make their own decisions, function autonomously in a way that ISS crews never do. This isn't a minor adjustment. It's a fundamental change in how space missions operate. It requires a different crew mindset, different training, different protocols. Mars crews would need to be comfortable making critical decisions without consulting Earth, accepting responsibility for outcomes good or bad, living with the isolation of knowing that in any emergency they're on their own, for at least the 8 to 48-minute communication round trip, plus whatever time it takes for Earth to analyse the situation and provide advice. Often, by the time useful advice arrives, the emergency is over one way or another. The political and governance questions are fascinating too, though often ignored in technical discussions of Mars missions. Who governs a Mars colony? Initially, it would probably operate like a research station with a commander designated by the sponsoring organisation, whether that's NASA, SpaceX, or an international consortium. The commander would have authority over mission operations, safety decisions, and resource allocation. But as the colony grows, as more people arrive, as children are born, as the population becomes more diverse, governance becomes more complex. Do colonists have political rights? Can they vote in elections on Earth? Or are they politically separate? If disputes arise, what legal system applies? If someone commits a crime on Mars, who has jurisdiction? These questions don't have clear answers because there's no precedent for permanent human settlements outside Earth. The Outer Space Treaty of 1967, which most spacefaring nations have signed, states that no nation can claim sovereignty over celestial bodies, including Mars, but it doesn't prohibit settlement, and it's unclear how governance would work under the treaty. Would a Mars colony be under the jurisdiction of whatever nation sponsored the mission? Would it be internationally governed like Antarctica? Would it eventually claim independence as a separate political entity? That last option seems far-fetched initially, but over decades or centuries it becomes plausible. A population of humans born on Mars who have never been to Earth, who consider Mars their home, might eventually assert political independence from Earth. They'd argue that Earth-based governments have no legitimate authority over people who don't live on Earth, who don't use Earth resources, who face unique challenges that Earth governments don't understand. This could create political tensions or even conflicts. Would Earth recognise Mars' independence? Would some nations support it while others oppose it? Would there be economic disputes over resources extracted from Mars or trade between planets? These seem like distant concerns, but they are worth considering because they affect how we establish colonies initially. The political framework we create now will shape Mars development for centuries. If we establish colonies as extensions of Earth nations, we create potential for future conflicts over jurisdiction and resources. If we establish colonies as independent entities from the beginning, we create challenges around funding and support, since Earth governments will be less willing to invest billions in settlements they don't control. If we establish international colonies, we create complex governance challenges around decision-making and authority. There's no perfect solution, only trade-offs and compromises. But these decisions will have to be made, and they'll affect the lives of everyone involved in Mars colonization. Let me return to the core question we started with: why anyone who goes to Mars will never come back. We've explored this from multiple angles. The physics of fuel and propulsion make return trips exponentially more difficult than one-way trips. The biology of human bodies in space makes 3-year missions potentially irreversibly damaging. The economics make one-way missions 5 to 10 times cheaper, allowing more people to go and more infrastructure to be established. The psychology of permanent settlement creates self-selection of volunteers who accept exile. The timeline of orbital mechanics and technology development favors beginning colonization now rather than waiting for better return capability. The practical realities of life support, resource extraction, and mission operations require treating Mars as a permanent destination rather than a temporary visit. The social and political complexities of long-term settlement reinforce the need for permanent commitment rather than short-term exploration. All of these factors converge on the same conclusion. Mars missions that actually happen, that get funded and launched and carried out, will be one-way missions. They'll be colonization efforts, not exploration missions. The people who go will be saying goodbye to Earth forever. This isn't a failure of imagination or ambition. It's an acceptance of physical reality. The universe imposes constraints. Distances are vast. Fuel requirements are exponential. Human bodies are adapted to Earth conditions. And changing any of these factors requires technologies we don't have and might never develop. Within these constraints, one-way missions are achievable. We have or can develop the technology to land people on Mars and keep them alive. We can establish permanent settlements that grow over time with continued support from Earth. We can begin the long process of making humanity a multi-planet species. But we can only do this if we stop pretending Mars missions will look like Apollo missions. If we stop planning for return trips that are prohibitively expensive and difficult. If we accept that the first generation of Martians will be people who leave Earth forever to build something new on an alien world. Mars colonists will be continuing that tradition. They'll be leaving Earth to establish humanity's first settlement on another planet. They'll face challenges and hardships that will kill some of them. The ones who survive will build something new, something that has never existed before, a human society on an alien world. They won't return to Earth, but their legacy will. Everything we learn from Mars colonization will inform future efforts. Technologies developed for Mars will have applications on Earth. The experience of establishing a self-sufficient settlement in a hostile environment will teach us things about sustainability and resilience that we can apply everywhere. Let me address some of the specific technological challenges in more detail, because understanding these helps clarify why return missions are so difficult while one-way missions are feasible. The propulsion technology available today is chemical rockets. We burn fuel, generate thrust, and accelerate spacecraft. This technology has fundamental limitations imposed by chemistry. Chemical reactions release a specific amount of energy per kilogram of fuel, and that energy determines how much velocity change you can achieve. The best chemical propellants currently in use are liquid hydrogen and liquid oxygen, which power rockets like the Space Launch System and the upper stages of various launch vehicles. These propellants provide a specific impulse, measure of efficiency of about 450 seconds. This means 1 kilogram of propellant can produce 4 kilograms of thrust for 450 seconds before being exhausted. This is good as chemical rockets go, but it's still limited. To achieve the velocity changes needed for Earth to Mars to Earth journeys requires enormous amounts of propellant relative to payload mass. The rocket equation is unforgiving. Methane and oxygen, which SpaceX plans to use for Mars missions because they can be manufactured on Mars, have slightly lower specific impulse around 370 seconds. This is acceptable, but makes the propellant requirements even larger. Alternative propulsion technologies exist in theory or early development, but aren't ready for crewed missions. Nuclear thermal propulsion, where a nuclear reactor heats propellant to create thrust, could provide specific impulse around 900 seconds, roughly double that of chemical rockets. This would significantly reduce propellant requirements for Mars missions. NASA and other agencies have researched nuclear thermal propulsion since the 1950s. Prototype engines were built and tested in the 1960s and 70s. The technology works, but it's never been flown in space because of political concerns about launching nuclear reactors and the expense of developing flight-qualified systems. If nuclear thermal propulsion were available, Mars return missions would be more feasible because you'd need less propellant, which means less mass, which makes the entire mission more manageable. But developing, testing, and qualifying nuclear thermal propulsion for human spaceflight would take at least a decade and cost tens of billions of dollars. It's not impossible, but it's not imminent either. Without it, we're stuck with chemical propulsion and its limitations. Electric propulsion, which uses electrical power to accelerate propellant to very high speeds, provides even higher specific impulse, thousands of seconds in some cases. But electric propulsion produces very low thrust. It can accelerate cargo slowly over months or years, which is fine for unmanned missions, but it can't support rapid transit of human crews who need to minimize radiation exposure and life support duration. You can't spend 2 years accelerating to Mars and another 2 years decelerating. The crew would be dead from radiation exposure or system failures long before arrival. So for human missions in the near term, we're limited to chemical propulsion with all its disadvantages. This makes return missions exponentially harder than one-way missions because the propellant requirements are so massive. The life support technology also deserves deeper examination. Keeping humans alive in space requires recycling air, water, and managing waste in closed-loop systems. The ISS, Environmental Control and Life Support System, or ECLSS, represents the current state of the art. It recovers about 93% of water from all sources, including humidity, urine, and crew hygiene water. It removes carbon dioxide from the cabin air and uses it along with hydrogen to produce water and methane through the Sabatier process. The oxygen from the water is released back into the cabin air while the methane is vented overboard. This system works but requires regular resupply of consumables and replacement parts. Over a year of operation, about 900 kilograms of supplies need to be delivered to maintain the system. For a 3-year Mars mission, you'd need similar systems, but with higher reliability and less dependence on resupply. This requires improving recycling efficiency and increasing system redundancy. Recovering 93% of water sounds good, but 7% loss over 3 years is substantial. For a crew of 6, that's several tons of water that need to be replaced, which means either carrying it from Earth or extracting it on Mars. Achieving 99% recovery efficiency, which would reduce losses to manageable levels, requires more advanced systems that haven't been fully developed and tested yet. Similarly, the ECLSS requires power about 10 kilowatts continuous draw for a crew of 6. On the ISS, this power comes from large solar arrays. On Mars' surface, power generation is more challenging. Solar panels work but are less efficient on Mars than in Earth orbit because Mars is farther from the Sun and receives only 43% as much sunlight as Earth. Dust storms can further reduce solar panel output. A Mars colony would need either very large solar arrays or nuclear power to ensure reliable energy supply. Nuclear reactors provide consistent power regardless of weather or time of day, which makes them attractive for Mars bases. NASA has developed kilopower reactors that can produce 10 kilowatts from compact uranium-fueled systems. Several of these could power a small Mars base reliably. But like nuclear thermal propulsion, nuclear power systems face regulatory and political challenges. Launching nuclear material requires extensive safety reviews. Public concerns about nuclear accidents during launch or landing create political obstacles. These aren't insurmountable, but they add time and cost to mission development. The thermal control challenges on Mars are also significant and often underestimated. Mars' surface temperature varies wildly. At the equator during summer days, temperatures can reach 70 degrees Fahrenheit, but at night they plunge to minus 100 degrees Fahrenheit or colder. Near the poles, temperatures can drop below minus 200 degrees Fahrenheit. Keeping habitats at comfortable human temperatures around 68 to 72 degrees Fahrenheit requires active heating and cooling. During the day, you might need to reject excess heat from solar gain and equipment operation. At night, you need to retain heat and possibly add heating to maintain temperature. This thermal cycling every Martian day, which is 40 minutes longer than an Earth day, stresses materials and systems. Seals expand and contract. Metal components experience thermal fatigue. Everything needs to be designed to withstand this daily temperature swing for years without failing. The radiation shielding problem is particularly difficult to solve. On Earth, we are protected by the atmosphere, which provides shielding equivalent to about 10 meters of water. On Mars, the atmosphere provides shielding equivalent to about 20 centimeters of water. That's 50 times less protection. To achieve Earth equivalent protection on Mars, you'd need to bury habitats under several meters of regolith, or surround them with water tanks. Both approaches add complexity and cost. Excavating and moving regolith requires heavy equipment. Manufacturing and filling water tanks requires water extraction and purification capacity. Early habitats will probably accept higher radiation exposure than ideal, because the alternatives are too resource-intensive. Over time, as the colony grows and develops more capability, better shielding can be implemented. But initially, colonists will live with elevated radiation exposure, accepting increased cancer risk as part of the cost of being on Mars. The medical challenges of a Mars colony are sobering when you consider them in detail. On Earth, if you get sick or injured, You can access medical care ranging from basic first aid to sophisticated hospital treatment. On Mars, the crew would have only the medical supplies and equipment they brought with them. For minor issues, cuts, burns, infections, this is manageable with a well-stocked medical kit and training. All crew members would need medical training, at least at the EMT or paramedic level. One or more crew members would need more advanced training, possibly physician level, to handle more serious problems. But there are limits to what's treatable with limited resources. Appendicitis requires surgery, and while a trained surgeon could theoretically perform an appendectomy in a Mars habitat, it's extremely risky without proper facilities, sterilization capabilities, anesthesia, and post-operative care. Broken bones need to be set and immobilized, which is possible, but complications like infections or improper healing could be permanently debilitating. Dental problems are particularly concerning because they can become severe quickly and are painful and debilitating. A serious tooth infection could kill someone if untreated, and treating it requires dental equipment and expertise that might not be available. Chronic conditions are also problematic. What if someone develops diabetes during the mission? They'd need insulin, which requires refrigeration and has limited shelf life. Do you bring enough insulin for potential diabetics in the crew for 3 years or longer? What about other chronic conditions that might develop? Heart disease, kidney problems, autoimmune disorders. Many of these require ongoing medication or treatment that simply won't be available. The crew would need to be selected for excellent health, but people can develop medical problems unpredictably. And pregnancy, whether planned or accidental, presents enormous challenges. Do you allow pregnancy on Mars? If so, you need prenatal care capability, delivery assistance, which could require caesarean section capability in case of complications, and postnatal care for mother and infant. An infant on Mars would have unique needs, including adapting to the low-gravity environment during critical development phases. We have no data on how human development proceeds in Mars gravity. It might be fine, or there might be serious developmental problems. The first Marsborn children would be experimental subjects in an unplanned medical study with no way to intervene if problems arise. This ethical complexity is part of why most mission planners assume the first missions won't include children, but enforcing that over years or decades of settlement is difficult. If you have a permanent colony with adults of reproductive age, eventually pregnancies will occur. Whether planned or not, you either prepare for that possibility or accept that colonists are making choices that could end badly. The comparison to historical human migrations and settlements is instructive, but also reveals important differences. When Polynesians settled the Pacific Islands, they undertook dangerous ocean voyages to reach uninhabited lands. Many expeditions failed, people died, boats sank. But some expeditions succeeded and established populations on remote islands. The difference is that once Polynesians reached an island, the environment was livable, the air was breathable, the temperature was tolerable, food could be found or grown. Water was available from rain and streams. The islands were harsh in some cases. Resources were limited, but they were fundamentally habitable for humans without technological support. Mars isn't habitable without technology. Without a pressurized habitat providing air, you die. Without thermal control, you freeze or overheat. Without water extraction and purification, you dehydrate. Without food production or stored supplies, you starve. There's no living off the land on Mars because the land doesn't support life. European colonization of the Americas is another common comparison. Europeans crossed the Atlantic, a dangerous journey that took months and killed many passengers through disease, storms, and shipwrecks. But those who survived arrived in environments where they could breathe the air, drink the water, hunt game, and grow crops. The land was inhabited by indigenous peoples with established civilizations, which created moral complexities and conflicts that we now recognize as colonialism with all its evils. But from a purely survival perspective, the Americas were habitable. Colonists could survive with relatively simple technology, basic agriculture, simple tools. Mars requires continuous technological support. Every moment of life on Mars depends on systems functioning correctly. A failure in power generation, life support, thermal control, or pressure maintenance means death within hours or days. You can't retreat to simple living if technology fails. There's no subsistence farming on Mars, no hunting and gathering, no traditional survival skills that help if modern technology breaks down. You either maintain technological systems or you die. This makes Mars colonization fundamentally different from any historical human migration. It's more similar to permanent undersea habitats or space stations than to settling new lands on Earth. You're not moving to a new environment where you can live naturally. You're building an artificial environment and living inside it completely dependent on it continuing to function. This question of how many missions and colonists would be needed to establish a viable colony is worth exploring. A single mission with 6 people isn't sufficient. They can survive, conduct research, establish initial infrastructure, but they can't build a self-sustaining society. You need more people for skill diversity. Medical professionals, engineers, scientists, agricultural specialists, technicians, maintenance workers. You need genetic diversity for long-term population sustainability. You need enough people that accidents or deaths don't doom the entire colony. Estimates vary, but most analyses suggest a minimum viable colony would need several hundred people, possibly 1,000 or more. This allows for sufficient skill diversity, genetic diversity, and social complexity to create a functioning society. It also provides enough labour to maintain and expand infrastructure without everyone being constantly overworked. Building a colony of several hundred people requires many missions over many years. If each mission carries 6 people, you'd need 50 missions to reach 300 colonists. At 1 mission per launch window, that's over a century. Even if technology advances to allow larger crews, perhaps 20 people per mission, that's still 15 missions, 30 years of continuous effort at 1 mission per launch window. This long time horizon is part of why Mars colonization is daunting. It's not a single project that succeeds or fails based on 1 mission. It's a multi-generational effort requiring sustained commitment and resources over decades. Political administrations change, budgets fluctuate, public interest waxes and wanes. Maintaining focus and funding for Mars colonization over 30 to 50 years is extraordinarily difficult. This is another reason why framing missions as one-way colonization rather than round-trip exploration makes practical sense. Exploration missions are evaluated on whether they succeed, whether the crew returns safely, whether they collected valuable data. If a mission fails, the program might be cancelled. If a mission succeeds but doesn't seem worth the cost, future missions might not be funded. Colonization missions are evaluated differently. Each mission contributes to building a permanent presence. Even if individual missions face challenges or losses, the overall goal of establishing a colony continues. The success metric isn't whether everyone comes home, it's whether the population on Mars grows and becomes more self-sufficient over time. This framing might be more sustainable politically and economically because it's a long-term investment, rather than a series of expensive one-off missions. Think about the knowledge and skills that would be valuable on Mars. Obviously, engineering skills, mechanical, electrical, systems engineering, all critical for maintaining and repairing equipment. Medical skills from basic first aid to surgery if possible. Agricultural skills, growing food in controlled environments with limited resources. But you'd also need skills we don't usually associate with space exploration. Welding and metal fabrication for repairs and construction, programming and software engineering. Because so many systems depend on software chemistry for analyzing materials and processing resources. Geology for understanding Martian terrain and resource deposits. Psychology and conflict resolution for maintaining social cohesion. Teaching because if the colony has children, someone needs to educate them. Cooking because food morale is important for psychological health and crew cohesion. Art and music because humans need more than survival. They need meaning and beauty and culture. A Mars colony would need a diverse population with a broad range of skills, and colonists would need to be cross-trained in multiple areas because the population would be too small for narrow specialization. Everyone would need basic mechanical skills to assist with repairs. Everyone would need basic medical training to help in emergencies. Everyone would need basic agricultural knowledge to assist with food production. This generalist approach is different from modern Earth society where people specialize deeply in single fields. Mars would require Renaissance people, individuals with broad knowledge and multiple capabilities who can adapt to varied challenges. Finding and training such people would be part of the selection process, favoring those with diverse backgrounds and demonstrated ability to learn new skills. Let me close by exploring what success would actually look like for Mars colonization. It's not bringing people back to Earth. Success is establishing a permanent, growing, increasingly self-sufficient human presence on Mars. Success is measured in decades and centuries, not in single missions. The first mission that successfully lands colonists and keeps them alive is a success, even if those colonists never return. The 10th mission that adds more colonists and more capability is a success. The 50th mission that delivers the infrastructure needed for a colony of 500 people is a success. A century from now, if there are thousands of people living on Mars, born there and raising their own children, building a society and culture distinct from but connected to Earth, that would represent complete success for Mars colonization efforts. Those people would look back at the first colonists, the ones who left Earth knowing they'd never return as founders and heroes. They tell stories about the courage required to be first, to face the unknown, to accept permanent exile for the possibility of creating something new, and they'd be grateful because those first colonists' willingness to go one way made Mars home for future generations. This long view is essential for understanding Mars colonization. It's not about the first mission or the first landing or the first few years. It's about starting a process that unfolds over centuries that transforms humanity from a single planet species to a multi-planet species that creates new human societies in new environments. The people who go first won't see the end result. They'll see the beginning, the foundation, the first steps, but they'll know they're part of something larger than themselves, something that will outlive them and justify their sacrifice. And eventually, if the colony succeeds, if it grows and thrives, there will be Martians, human beings who were born on Mars, and consider it home. They'll look up at the night sky and see Earth, a blue dot among the stars, and they'll know that's where their ancestors came from. But Mars will be their world, and they'll build their own culture, their own society, their own future under red skies with 2 small moons orbiting overhead. This has been a long journey tonight, exploring why anyone who goes to Mars will probably never come back. It's not a cheerful conclusion. There's something melancholy about the idea that the first Martians will be exiles cut off from their home world forever. But there's also something noble about it. They'll be choosing exile for a purpose, sacrificing their connection to Earth to establish humanity's presence on another world. That takes a special kind of courage. Not the courage to face danger and overcome it, though that's required too, but the courage to leave behind everything familiar and embrace a future that's unknown and uncertain. The courage to say goodbye forever to everyone and everything you've known. To trade Earth for Mars, to become something new. Throughout history, humans have made these kinds of choices. We've left our birthplaces to seek new opportunities, to escape danger, to explore unknown lands. Some journeys were forced by circumstance. Some were chosen for adventure. All of them required leaving something behind. Mars is just the next step in that long history of human migration and exploration. A bigger step, yes, a more permanent step, but fundamentally the same impulse that's driven humans to spread across Earth. The difference is that this time we're leaving Earth itself. We're becoming an interplanetary species. And that transformation requires pioneers willing to be the first to take the risks, to accept that they're closing a door behind them that will never open again. So the answer to the question posed at the beginning is clear. Anyone who goes to Mars will likely never come back because the physics, biology, and economics of return are prohibitively difficult. While the case for permanent settlement is compelling, the first Mars missions will be colonization missions, not exploration missions. The first Martians will be colonists who accept permanent exile in exchange for being part of something larger than themselves. And while this might sound bleak or tragic, it's also the only realistic path forward. If we wait for the technology and resources to make round-trip missions routine, we'll wait forever. If we accept that colonization means permanence, we can begin now. The first humans could land on Mars within 10 to 20 years. They could establish a base, start extracting resources, begin growing food, and lay the foundation for a settlement that will last centuries. Within our lifetimes, there could be people living on Mars, people who will never see Earth except as a distant point of light in their night sky. That's both sad and magnificent. Sad because they'll never come home. Magnificent because they'll be building a new home for humanity among the stars. Thank you for staying with me through this long exploration of Mars and the reality of interplanetary travel. If this changed how you think about Mars missions, about space exploration, about what it really means to become a multi-planet species, then the time was well spent. The conversation about Mars is often dominated by optimism and ambition, which are valuable, but it's also important to be honest about the challenges and the costs. Going to Mars isn't like going to the moon. It's more like leaving your home country to settle a harsh frontier where no help is coming if things go wrong. It requires a different mindset, a different kind of commitment. And the people who make that commitment, who volunteer to be the first Martians knowing they'll never return, will be among the most remarkable humans who ever lived. They'll be choosing the unknown over the familiar, choosing hardship and risk over comfort and safety, choosing to be pioneers in the truest sense of the word. We should honour that choice, support it with resources and technology, and recognise it for what it is, the beginning of humanity's transformation from an Earth species to a solar system species. One day, perhaps centuries from now, there will be thriving cities on Mars, domed settlements under red skies, people who have never seen Earth, living full, rich lives on our neighbouring planet. They'll tell stories about the first colonists, the ones who left Earth forever to make Mars home, and those stories will be about courage and sacrifice and vision, about people who gave up everything to build something new. The first Martians won't come back, but their legacy will echo across generations, and in the end, that might be the most important journey any human has ever taken. Good night, and thank you for exploring this with me. The future is being written now, and it's more complex and more challenging than most people realise. But it's also within reach if we're willing to accept the reality of what interplanetary colonisation actually requires.